So our next presenter is actually going to be Deborah Domingue, doing her talk on Regolith structural characterization of lunar swirls within Mare Ingeii. And I do apologize, but I don't have the same bell sound as you, so your timer is going to be a little bit different sounding.
That's okay. I will try to respect the time. So I'm assuming people could see my slides, yes?
Yes.
Okay, so let's see. So this is a project I've done with several of my colleagues at PSI, and we're taking a look at the structural characteristics of on versus off swirl. The goal is, can we see evidence for structural differences? Are they more consistent with the space weathering hypothesis that Dave described? There's another idea for their formation that involves dust levitation. Is it more consistent with that, or is it a bit of both? The methods we applied, we did topography using stereophotoclinometry. And this is a method that's used for spacecraft navigation to identify landmarks. It has the ability to get very high topographic and therefore incident emission phase angle information on a pixel by pixel level for the images we used. We applied a photometric model. I'm one of Bruce Hapke's students, so guess which model I applied. So we looked to basically see, do we get the same values on swirl as off swirl? And can we correlate the modeling results with structural characteristics? So here's my story. Why is it important? We really do want to have an understanding of how these features form. Dust is everywhere. One of the things for going back to the moon is, how do we deal with that? And what kind of mobility does it have? Because we're going to have to design our habitats, our equipment, our protective gear for our people with that in mind. It is one of those environmental issues that we're going to need to deal with. And what can the structure of the regolith tell us about these features that the spectroscopy hasn't already told us? So what are the relative roles of these two processes? So I already mentioned this. We use stereophotoclinometry to co-register images and to provide a high fidelity and a high spatial resolution for our topography, which in turn means we can derive the photometric angles, the changes in incident emission due to topography. And that is very time inclusive and time intensive. So instead of doing the whole Mare, we took a look at this little swirl here, this little tail within Mare Ingeii. And one of the things when you do a photometric study is you look at the quality of the data. And what I mean in terms of quality of the data is, does it cover enough of the incident emission and phase angle space to be able to constrain the parameters? Is this going to be able to give you viable solutions? And this is a data quality map of our region. Green is great, blue is good, red is eh. That's what you need to take away from this slide. And basically what it does, how we determined that is we looked at how many bins of angle range. So for every degree of incident emission, did I have data in that bin? And out of all the bins that I could have, how many bins did I cover? So it's a simplistic way of looking at the coverage. Oh, great, my slide now doesn't want to work. Okay, so we used Hapke's model, and for anybody who lives, eats, and breathes photometry, there are pros and cons to Bruce's model. There are others out there that can be used to characterize the surface. But what this one does is it allows us to compare one region to another, and it allows us to correlate parameters with surface properties. This particular model is based on radiative transfer. The different components of the model are correlated to or derived from physical mechanisms, um, physical processes, scattering processes. So there is a minimum, a theoretical correlation between the parameters and different physical properties. In the lab, we've shown that the parameters aren't uniquely just this property and this property alone. So when we interpret their values, we keep in mind what the laboratory tests have shown us, that different physical structures can impact the parameter value. So you need to keep those in the back of your mind. We just did a simplest approach, least squares grid search. We varied all the parameters simultaneously. And these are our results. Yay! What am I looking at? All right. So going from left to right, what we have is a map of the single scattering albedo, a map of the phase function, the scattering function, and then a map of the surface roughness. Right. So I'm going to go through each of these in order. So in the lower right-hand corner, you see an albedo map of the swirl region. And if you can see my cursor, here's the nice little curly Q tail that we were looking at. This is on swirl. Oops, nope. And this is off swirl. And you can see, despite all the different data quality regions, and they do map, you can see the swirl in the single scattering albedo map. Once again, if you look at the scattering function, however, you see it in the albedo, this is where it is. We do not see the swirl being brought out in the value of the scattering function parameter. So this tells us no correlation. The particle scattering function is correlated to particle structures and interparticle relationships. And we're not seeing variations between on swirl and off swirl here. Surface roughness, once again, we should see our little curly Q here, and we don't. So there's no variations in what I call granular topography. Surface roughness as defined within this model correlates to the optically active portion of the regolith. So we're talking about a few microns deep here. So we're talking about on the order of millimeters at most. So we're looking at how the topography on the grain level. So once again, no correlation. So I'm going to summarize here real quick what we think in terms of expectations for space weathering versus expectations from dust levitation. And to me, this would make a good discussion. We see variations in the single scattering albedo, and we would expect that whether it's from space weathering or from dust levitation. The dust levitation model, since that has not been discussed too much, supposes that we have a fine grained feldspatic portion that is preferentially placed in the bright swirl region. So feldspar is brighter than is the brightest portion of the regolith. So that's why we would see the correlation with single scattering albedo. The scattering function variations, we would expect to see differences in grain structure from space weathering. We expect to pick up radiation damage in the grain structure, but we don't see it correlated here. So that's why we have the red X under for space weathering. We don't expect too much difference in grain structures between on swirl and off swirl with the dust levitation model. And as far as surface roughness, we don't expect the space weathering to change the surface roughness, but we would expect it to see it in dust levitation because you would have a finer grain component being overlain on the topography of the the coarser grains. So we have some pros for both and some cons for both hypotheses. But once again, we only took a look at a little area. So our next step here is to go and take a look at a larger area, one that shows more dynamic variations in albedo. And stay tuned. We've just finished building the topography for this region, and now I just need to run it through the photometric model. And hopefully within a month or so, we will be able to compare and contrast those two regions and see if they tell us the same story.
Oh, right. You are just about out of time, but we do have
Okay.
time. We have time for a couple questions. We have a couple minutes left.
All right.
So does anybody have any questions?
Okay, so I can't see the chat box with my when I share slides, so I'm going to stop sharing.
Oh, I can read you the questions as well.
Okay. Okay.
Paul Sanchez asks, "What do you mean by granular topography?"
Okay, so most people, when they think of topography, they think of, okay, I'm going up on this ridge and I'm down and I'm flat here, and oh, here's the topography of a crater. That's large scale. When I talk about granular topography, think about I have this rock here and I have this rock here. Now all of a sudden I have this kind of topography. So it's small scale topography. Does that make sense? So that when I say granular topography, that's the kind of thing I'm talking about. I'm talking the roughness that the particles themselves create on the surface. So when let's say this is my rock A, rock B, or grain A and grain B. If I've got a fine grain, so I have this kind of roughness. If I have a piece of fine grain dust come in and sit in over here, it's going to even out this topography. So that's why I had expected, if dust levitation was playing this big role, I would have seen a change in roughness.
Okay, so Paul said yes, but that requires a very high resolution. And do you have that kind of data?
Okay, so if you
We'll
look,
have about 1 minute left.
okay, all right, so I'll try to answer this real quick. So when you look at the derivation of the roughness parameter in the model, the roughness parameter is basically an average from the footprint size of your detector down to the particle scale. And Paul Helfenstein took a look at some of the Apollo images to try to say, okay, at what scale are we really talking about when we look at this Hapke roughness parameter? And he determined it was probably the centimeter scale centimeter to millimeter scale was dominating the roughness that this parameter referred to. Does that answer your question? So we're thinking we're being dominated by millimeters to centimeter scales here with our data set.
Okay, Paul says yes, that does answer the question. And there are quite a few other questions, but we are out of time. So if anyone has extra questions, I believe you could email if that's all right with you.
That's great if you could, because I won't have time to answer them in the chat because I do want to pay attention to the talks in this session as one of the co-chairs. So, but I want to say thank you for the interest.